morning, everyone.
Sorry.
We are starting now the morning session of the second day of the conference. So it's a pleasure to have the Zoom talk by Markus Arndt, and who is talking from the University of Vienna. So Markus, please, you can get started. Thank you.
Okay. Yeah, thank you very much for inviting me even online. It's a long distance and I would have loved to come, but it's a pleasure to be here online at least. So it's also an interesting meeting in the sense that it's about quantum and gravity. And I have to be honest, of course, gravity plays a role, but so far mostly in that our particles fall. And of course, we don't yet see any indication of quantum gravity, just as a preliminary warning. But there's some progress in matter wave interferometry with higher masses, and that is what I would like to show to you. And of course, in the back of all that, there's a bigger team that you can see here in our university. There's also funding, in particular by the FWF and the Moore Foundation, and for future projects also by the Office of Naval Research. And so here we go with science. So I'm not sure how many MetaWave talks you had already. I forgot to look into the program of yesterday, but just as a reminder, because we have the year 2024, which is almost 100 years after the discovery or the hypothesis of Louis de Broglie, that there should be matter waves, that there should be something like wave nature of any massive object in motion. And that was a very bold hypothesis in 1923. And as we all know, it has become truth in many and proven with many different particles, starting from electrons in 1927, atoms and small molecules, dimers in 1930, and even neutrons, which were only discovered in 1932. Then 1936, already some first diffraction experiments. And with atoms and dimers and Bose-Einstein condensates, this really took off in the middle of the 80s and really a lot in the 90s. And now this is a huge field where you can study complex quantum systems, many-body systems, coherent systems, atom lasers, and very macroscopic systems, quantum systems. But that is what I'm not going to talk about. Because these things are ultra cold and ultra isolated and individual atoms all in a coherent mode, but nonetheless individual atoms with a de Broglie wavelength corresponding to individual atoms. What we've become interested in already since 1999, a little bit earlier, is to look into systems which are covalently bound, van der Waals bound, metallic cluster bound, which can be supermassive as a single particle, but composed of dozens of atoms up to thousands of atoms, and most recent experiments, tens of thousands of atoms, and where this single, almost classical body can be delocalized as a quantum object. So it's really the extreme opposite end of the scale, where the number of atoms is comparable to Bose-Einstein condensates, but where the internal temperature is more of the scale of a few Kelvin instead of nanokelvin, so 9 orders of magnitude in between, or 10. The binding energy on the scale of electron volts instead of nanoelectron volts, again, 10 orders of magnitude in between. And the de Broglie wavelength is accordingly also much, much smaller, and the smallest that we currently run is of the order of a few 10, 20 femtometers, which is much smaller than the particles that we're looking at, which are typically of the order of a few nanometers up to 10 nanometers or so in diameter. So again, orders of magnitude smaller de Broglie wavelength than particle size. And nonetheless, these particles can then be delocalized in our experiments on the scale of hundreds of nanometers. So much bigger than, much wider than the individual particle. And so the rest of the talk is, so to say, the story about the journey to get there. To the particles that you see in front of you, the fullerenes were very early, so I will hardly talk about this. Then the tailored macromolecules, which are still interesting, clusters which are really at the focus at the moment, and proteins which are coming up. It's still a lot of experimental work, but we'll briefly talk about that. So why are we doing this? And people here in this audience, as the name says, are mostly interested in quantum and aspects of gravity. That is also what kind of triggered us in the very beginning to see How do we get to higher masses, higher complexity? Is there anything like gravitational collapse, spontaneous collapse, and things like that? But of course, in order to get there, you have to really go to very high masses, which are still very demanding, I believe, for all experimental groups. But that is kind of one of the prime goals, to understand what is the difference between the quantum phenomena and classical phenomena. Is there any substantial difference? Is that a gradual transition? Are there rules that change in this world, so to say? So quantum macroscopicity and decoherence is a big issue. And that may be independent of gravity. There may be entirely different agents at work, even preventing that one eventually gets to testing gravity, maybe. But let's see. Then we have a branch that is interested in biophysical chemistry, because we do experiments with complex molecules, with organic, biological molecules. I'll skip this for today. That's not at the focus of this talk. There's an applied aspect, again, that I will skip for today, where we are interested in generating metallic nanostructures in matter wave lithography. Gravity physics, that's a story that we can talk about quite in length. I don't have so many gravity results. That's why I will not overemphasize this, but probably allude to some aspects where I need help, theoretical help, to see whether we find interesting directions of future research. And there's condensed matter physics inherently in everything we do, because now with our metal clusters, these are little solids, little condensed matter blocks, and they have interesting properties that change as a function of their scale. So they have internal quantum properties, and those internal quantum properties are relevant for their quantum delocalization in our interference experiments. Last but not least, but that is a very far shot, so to say, like testing gravity, I should say, to probe dark matter, testing non-standard physics, and so forth. That is all extremely demanding and not what I can talk about today. So in all these experiments, I typically say we have 3-4 challenges to have a good source, very intense, brilliant, cold, mass selected, and so forth source. Then we need coherent beam splitter technologies, interferometers, detectors, and of course we also have to avoid decoherence. And I don't want to dive too deeply into beam splitter technologies, because that's a long story, because atom interferometry has a long history now. Just to give credit to the people in atom interferometry, which started this already in the 80s, like Dave Pritchard, very, very early on, with optical gratings, nanomechanical gratings. And then later, Christian Bordet, actually, he thought about this in 89, but had experiments in 81. To use single photons as beam splitters, Rabi cycles as beam splitters, and Kasevich and Chu for Raman beam splitters. So many things were developed in this field. Many elementary things were developed in a few years between the mid-80s and beginning of the 90s. And since then, super important atom interferometer experiments have developed in all parts of the world, and I will briefly come back to that later. I just want to mention this here because many of these techniques we cannot use. Nanomechanical gratings we can use, as you will see, phase gratings we can use. We can also use single photon beam splitters, but based on a different technology. And this is what I want to briefly just mention here before we get gradually to the bigger and bigger things. So this is by now a small molecule, phthalocyanine, which is only 514 mass units heavy. And as you can see, there are a few dozen atoms involved that can be diffracted at, for instance, nanomechanical structures as you can see them. You see nanomechanical gratings, which were written with electron beams or gallium ion beams, even down to single atomic layers of graphene, where you can write a lattice, a grating into a graphene monolayer. And on the right-hand side, you see some of the diffraction patterns that you get. So that definitely works. That's a good thing. And it's universal in the sense that it works for different molecules or atoms. But there's an inherent limit, and that's the van der Waals force and charges sitting in the grating. So that's nothing that you would like to use on a protein, on a big cluster, on a nanoparticle. If you go to bigger and bigger masses, the nanomechanical gratings are getting challenging. So I'll skip these molecules. That's only to show that you can still do interesting things with them, but for higher masses, which are the focus of this meeting, that's not the way to go forward. Another trick that you can use, which was used in atom interferometry by Pritchard in the 80s already, is to use optical dipole gratings. And the idea there is simple, that anybody, so every massive body, every composite massive body is polarizable. So if you apply an electric field, it will develop a dipole moment. The dipole moment will talk to the electric field. D dot E is an energy divided by Planck's constant times a time. That is a phase. So you can impart a phase on the particle that passes through a standing light wave. It sees a different phase when it goes through the antinode or when it goes through the node of the grating. And that is something that was known for atoms already, even for electrons by Kapitsa and Dirac in the 30s of the last century. We did this together with Anton Zeilinger still in 2001 for the first time for fullerenes. And we're using phase gratings quite a lot nowadays, also for large systems, as you will see. And so that is something that works, to use not matter as a grating for light, but to use light as a grating for matter. Just as a fun remark, so to say, we've used this also on things that everybody probably has used in their lives already, like this antibiotic ciprofloxacin. I don't want to advertise the specific brand. I don't have any stocks. This is just to show this is something that everybody digests when they're sick, and these molecules, which are polar and complex, they can also be diffracted at light gratings. So that's kind of a fun fact. But this is scalable to larger things. Obviously, there's an inherent limit when the particles get much bigger than the grating period. That is no longer a good idea. But even for, say, 10 to the 6 mass units in gold, that's only 5 nanometers diameter. That is perfect. Or for sodium, 10 to the 6 mass units of the order of 10 nanometers diameter, that is still okay. Now, we will dive a bit deeper into near-field interferometry, because that is what we are currently and have always been using for higher mass interferometry, because the scaling is better than far-field diffraction. But in near-field interferometry, there's one very important precondition for the experiment to work, and that is that you have at least one structure that prepares coherence. Near-field means that you have spherical wavefronts from the beginning, so to say. But if you have no phase fronts, if you start from an incoherent source from the beginning, a spatially incoherent source, you have to prepare your coherence from the beginning. And for that, we always use what we call photodepletion gratings nowadays, which are gratings, optical gratings in the antinodes of which we can remove the molecules, the clusters, the nanoparticle from the beam. And this is important. It's a kind of, it's not interaction, well, I call it interaction free. There's a matter of debate, interaction free beam splitting, in the sense that, if I can take the mouse here, if the cluster or molecule passes here through the antinode, formally it doesn't see any light, but it knows that it has not seen any light, because if it had seen or would have seen the light here, it would have been ionized or by some other depletion mechanism be removed from the beam. So only those that do not see the light pass through. And because they can pass through, they have seen the grating, and this effect, this measurement-induced effect, is what we use for diffracting the molecules or clusters. It's a bit like the Elitzer-Weidmann detector, if you wish. And so it's not really a miracle, but it's a bit unusual compared to other beam splitters. And in this beam splitting mechanism, there's a momentum transfer simply because the grating has a periodicity of λ/2, wavelength of the light divided by 2. Therefore, the grating constant is λ/2, and the momentum transfer is 2 times the momentum of the photon. And there are different mechanisms, and that's the interesting about deep UV ultraviolet gratings. They're really universal in the sense that they can talk to almost everything. Of course, it still has to be tailored a bit, but it's pretty universal in the sense that if you want to have a metal cluster, interfering with itself, you can send it through such a grating. And in the antinodes of the grating, it will photoionize. So that's a very simple photodepletion mechanism because the ions are clearly distinguishable from the neutrals and they can be sucked out if you wish, so that only the neutrals pass through the antinodes, through the nodes. So that is a very straightforward grating mechanism for metal clusters that we are also using. Another mechanism, which is a bit more refined and that we take for biological molecules nowadays, is to use photocleavage, where friends in Basel, around Marcel Meyer and Valentin Köhler, functionalize specific organic molecules. That's only one example here. They functionalize these molecules, and if a UV photon hits this compound, it cleaves off a certain subcompound, then that can either lead to ionization or generally to fragmentation. And even the recoil during the fragmentation is enough to kick the molecule beyond the detector. So those that interact with the light are gone. If it's a more weakly bound cluster, which we had in the past, like caffeine clusters, vanillin clusters, so clusters of organic molecules, you can also just evaporate the entire cluster because the bond between them, the bond is so weak that the absorption of a deep ultraviolet photon is enough to dissociate the cluster, and then it's gone. And last but not least, it's not really the last mechanism, but it's an interesting mechanism also, which we are still planning to use. The other ones were demonstrated, but this is still to be used. Is like, for instance, photoisomerization of molecules. And now, in order to probe macroscopicity, you want to go to interferometry with more massive things. And here's what we have, an interferometer of the early days, where molecules were sent through a nanomechanical grating still in these days, an optical grating, a nanomechanical grating, and some detector. And the idea is always that the first grating prepares the coherence, does diffraction at a single slit, the second grating imprints the phase, and the third grating probes the interference. And already a while ago, this was scaled up to what we call a long baseline interferometer, which is really a 5-meter machine, 2 meters between the outermost gratings. As you can see, in high vacuum, 10 to minus 9 millibars in a big vacuum chamber, on an INVAR bar, 130 kilograms suspended from double pendulums, vibrationally isolated, and so forth. And well, the purpose of this large or long baseline is to be able to talk to very massive things. And the first setup that we had already a few years ago now was capable of going to 50 femtometers and masses of the order of 30,000 Dalton even when they were as fast as a plane, an airliner, 300 meters per second or 260 meters per second. And I will not spend too much time there, but just to say it's universal here in the sense that this interferometer could talk to atoms like alkali atoms, alkali earth atoms. It could talk to C60 and C70 molecules, polyaromatic hydrocarbons, radical molecules which had a dipole moment, peptides, smaller peptides, tripeptides. So it was really universal because it had mechanical beam splitters, a phase grating, and a mechanical beam splitter. So that's the old story where we pushed. Where we could more or less push up to 28,000 Dalton, and that used to be our mass record established in 2019. And this was a family of molecules of oligoporphyrines composed of between 1,800 and 2,000 atoms. They have these yellow dots at the outer rim, which are fluorine atoms, and the fluorine atoms were there to help the molecules evaporate if we laser desorb them. And these complex things, which had 5 nanometers in diameter and masses of the order of 25,000 to 28,000 Dalton, they showed, as you can see, very nice interference, high contrast interference in agreement with the expectations that we had in these days. So that was also already very interesting, but it's hard to scale this up. We tried actually together with Marcel Meyer in Basel, well, the chemists, they synthesized a number of metallic clusters with organic ligands to go to 100,000, 200,000 mass units. And some of them actually also flew, but the beam intensities were too lousy. So that in the end, we decided that's not the way to go to even higher masses. And so we had to set up something new to get to higher masses. But this organic stuff is quite interesting from a decoherence point of view because, well, every single particle is different from every other, but the de Broglie wavelength is still kind of very similar. And of course, you have always single particle interference, always a single particle interfering with itself. Voila. So in these days, just to make a case, I sometimes said, well, this is already a pretty massive Schrödinger cat. And we will discuss briefly other Schrödinger cats in a few slides. But so what do you need for a nice Schrödinger cat? It should be complex. In these days, I said it should at least have at least one biomolecule because that was the only Schrödinger cat with a biomolecule sitting inside, the porphyrins, which are biodies in hemoglobin. It should be warm, which it was, and it should be in different, clearly distinct states, being here and there at the same time, which it was, because the separation was 100 times, almost 100 times the diameter of the molecule. Well, the cat cannot survive without its natural environment. Actually, the molecule can. And the Schrödinger cat typically is something which symbolizes superposition and entanglement, superposition of being dead and alive, entanglement here in the case of entangling the cat with a radioactive atom. And well, this latter aspect is a little bit missing. We can generate the superposition without this entanglement to a radioactive atom. But I just wanted to make a case that you can also write down the Schrödinger cat, of course, as an entangled state, entangled with a vacuum, where all n atoms of the molecule, in this case 2000, are on the left-hand side with 0 in the other, or vice versa. So you can write it down as an entangled state. Whether it's a useful entangled state, that's a different matter, but it's clearly different from interfering a Bose-Einstein condensate, which would be written in this product state typically, where every atom interferes with itself, no matter how big the BEC is. Of course, you can try to generate entangled states in a BEC also, but that will be very, very hard to go to 2,000 or 10,000 atoms entangled this way. So that's the nice thing about molecular and cluster interferometry. You get this kind of entanglement for free, if you wish, in your superposition experiments. So yeah, this I mentioned already here, the distinguishability is the molecule having on the upper or the lower part of the experiment. And so far so good, but the question is, how do we move on from these complex molecules? They're already massive, but hot, fast, so what can we do? And yeah, before I go really to our experiments, I just wanted to make a brief case for what people call macroscopic nowadays. And so this is not to play anyone against anybody else. It's really only to find a landscape to place ourselves in. And you will see it's a rich field. This is only page 1 of it. So there's another page 2. And if you think, where do we have mesoscopic or macroscopic quantum aspects? Of course, there's a huge field of optomechanics where there's tremendous progress over the last decade, starting from cantilevers cooled to the ground state, really massive things. They're kind of macroscopic, cooled to the nanomechanical ground state, either cryogenically or optically cooled. There are nanoparticles of the level of 10 to the 8 Dalton in the ground state, even with expanded wave functions recently. And I think the most massive quantum ground state is a bulk acoustic oscillator in ETH, in cavity quantum acoustic dynamics in Yuan-Chu's experiments, where they have 0.5 milligram in the ground state. LIGO is an arguable case where they have effectively 10 kilogram in n equals 10, but it's not a single mirror, it's the relative motion of 2. But even Schrödinger cats were done, in this case by Yuan-Chu's group in ETH again, with a mass of 9 times 10 to the 18, so 16 micrograms. Supermassive Schrödinger cat, but with a very tiny, tiny delocalization of this state, only attometers. But a super cool experiment. If you compare that with ours, our masses are typically much smaller, but the delocalization much bigger. So it's not to play anyone against anyone. It's just entirely different regimes, and all of these experiments are cool. And if you ask what is the widest delocalization, quantum delocalization of things, then neutrons were pretty good already a long time ago. They could delocalize neutrons by 10 centimeters, which is impressive. And atom interferometry in Markasiewicz's group went up to 50 centimeters. And very soon, in various 100-meter fountains, I think they will go to 5 meters. If you think what's the longest coherence time, atom interferometry in Holger Müller's lab goes to 70 seconds. Nuclear spin coherence in nuclear magnetic resonance can go to 6 hours. So again, coherence times can vary about orders of magnitude. And so what is more quantum, you may ask? And there's no clear answer to that. You may ask, or you may say, well, it's more quantum if it takes me more effort, if I have to put in more H-bars, more H-bar Ks. And then atom interferometry is super cool because they have hundreds, thousands of H-bar K momentum, this separation between the two different arms. But then you could also say, well, if I can do this for atoms, I can also do this for photons. And for photons, you have entanglement of thousands, 1,200 kilometers, but without mass. Or angular momentum states of the order of 10,000 for orbital angular momentum, which is amazing. You could say, well, can I bring something into coherent field? Well, coherent is semi-classical, but at the same time for BEC, that's pretty quantum. A superfluid is pretty quantum. And there you can have anything from 10 to the 6 atoms per coherent field up to 10 to the 23 in a bucket of helium, liquid helium. So it can be super massive and quantum, and it's obviously helium is a quantum fluid. It shows quantum properties. And I will not be talking about entanglement for computing, for quantum computing at all, but that's where the billions nowadays go. And you may ask, how do I find an equivalence, or how do I map certain quantum algorithms in, if there are 400 qubits, how do I map this on the macroscopicity of a superposed virus or so? That hasn't been worked out theoretically even, how to make this analogy, how we would make a comparison of these systems. And so what we are doing at the moment here in Vienna is focus on what I call universal matter wave interferometry, that we try to do interference with atoms, molecules, peptides, proteins, nowadays metal clusters, dielectric clusters, to make it as universal as possible and see where we get. And mostly driven by this curiosity question, but also by a measure of quantum macroscopicity that I will get back to in a few moments. And, well, actually, no. So many of you may know and remember that Stefan Nimrichter and Klaus Hornberger defined a measure for quantum macroscopicity, and here the blue equation is just a shorthand for a much longer, much more elaborate theory, where they try to compare different systems from cantilevers to atom interferometers, and to distill a single number to say how well suited is this experiment to exclude certain non-standard models of quantum physics, where you have a small non-linear extension to the Schrödinger equation. So that's a very specific definition of quantum macroscopicity, only targeting the possibility of a small term non-linear extension to the Schrödinger equation. How well can you exclude this? And this is captured in this number mu. Forget about the detail, what it looks like, but just to give you an impression of what this means. So suppose you can do a matter wave interferometer with electrons, and you say, well, this is pretty quantum and that doesn't exclude much because the electrons are very light, so you expect that this should be quantum anyway. So you can exclude this small nonlinear term all the better, the more massive the particles are, the better the fringe visibility is. That's the logarithm of V over V naught, and the longer your coherence time is. And so it's favorable in this case for our experiments that this scales with a mass squared. So if you go from a single electron up to something that weighs hundreds of thousands of mass units, of course, there's a big factor to be gained. And if you ever get to, say, a mu of equals 16, then you would have to run an electron interferometer coherently for 316 million years to make the same exclusive statement about Schrödinger equation is still the only thing. There is no other term, no nonlinear term to be seen. And so what we are currently working on, and that is what I want to emphasize here in the rest of the talk, is that we're trying to get this orange dot confirmed and ratified, so to say. Our own experiments, this long baseline universal matter wave interferometer with the organic, the porphyrin derivatives, was kind of this little red diamond with, if you wish, kind of the record hold in the days of 2019. And the question is, how can we push this to higher masses? And of course, going to higher masses can go via trapped nanoparticles, and that's a big effort in a large community, and there's big progress also. You've heard Markus Arndt yesterday. Our experiments are different in the sense that we are still going for matter wave interferometry, simple, so to say, and delocalize massive things. And what we delocalize currently in these experiments are metal clusters. In a later stage, that should also again go back to silicon clusters, but here it's specifically sodium clusters. So sodium atoms aggregated into big clusters. And what we like about these experiments is that the idea behind it is really universal. It can be applied to a huge, vast class of materials, essentially all alkaline earths, and with an upgrade in the lasers, essentially also the coin metals and niobium and so forth. So it can talk to a number of different things, which makes it interesting for condensed matter research in nanoparticles. But here the key for the moment is to just in quotations, delocalize things. And what is nice about the metal clusters is at the same time their challenge, if you make them, you get all of them. I'll come to that in a minute. And that has the advantage that you can scale the mass from almost single atoms up to gigadalton if you wish. At the same time, collecting the right intensity in the right velocity class with the right mass selection is a challenge, to be honest. Okay, so what we've tried so far is to set up the experiment that you see with, there's Stefan and Sebastian and Philipp and Jakob and Bruno and Richard, and they were all working on this very intensely for a long time. And so we take sodium nowadays and put it in an oven, just a simple small oven heated to 500 C or so, and then it ejects sodium atoms, very dense cloud of sodium atoms. And that is ejected into a dilute gas of argon at about a millibar and 70, 80 Kelvin of temperature, so everything is like liquid nitrogen cooled. And in this cold atmosphere of argon, the sodium aggregates to clusters of various sizes. It has a log normal distribution, so it's a very broad distribution of clusters, which is good and bad at the same time. So we have all the masses that we want, and then have to select what we get. So this very intense cloud of particles is sent onto the interferometer, and the interferometer is a new one. It is composed of only deep UV ultraviolet gratings. So standing light waves of 266 nanometer laser light, that is a thing in itself to generate watt level, so 1 watt level of 266 nanometers that stay on that level for hours and days. So that's a task in itself. So it's a sub-team working on lasers. And then the clusters go through these nanogratings, and in the antinode of the nanograting, the cluster is ionized, singly, doubly, whatever, but as soon as there's a charge, it's extracted and gone. So only the cluster that passes the antinode, the node, where they do not absorb a photon, those clusters can pass through. Small difference in grating 2. Actually, we've reduced the intensity from order of magnitude 60 milliwatts to 5. And that is then sufficient that we can suppress ionization for certain cluster types, keep it low, and still use the phase grating effect. That there's an optical dipole in the clusters that is excited, and the interaction between the electric field and the optical dipole does also a phase modulation. The third grating does the detection of the interference pattern that forms. And well, actually, only an interference pattern, if an interference pattern forms, there's a regular structure that can go through. And if there's sufficient transmission, a mass spectrometer, again, based on photoionization and quadrupole mass spectrometry, can detect the particles and sort them by mass. So that sounds all very straightforward, and that's what we thought. And it's working to one degree, it's working extremely well, and I can show you a picture. So we see high contrast fringes, very high contrast, very high signal to noise of big metal clusters. And if we vary the grating laser power, we see that the fringe visibility changes in agreement with A theory. But, and that's the big but for the moment, it seems we were a bit naive in the beginning and overlooked that in the detector, not in the interferometer. Interferometer is fine, but in the detector, we do not only ionize them once, but also twice and 3 times and 4 times, because sodium clusters can be multiply ionized with the laser light we have. So the fringes that we see correspond actually to much more massive things than we thought. Now you could say, well, celebrate, this is great, because well, that's what we want to do. We want to have high contrast interference for massive things. And we have high contrast interference of massive things. But of course, you will also want to distinguish that this is definitely non-classical. There can also be moiré fringes. And as it turns out, and we never planned to have this experiment running at 1 million mass units, but the clusters that were actually in the experiment, as we found out in hindsight, were of the order of 1 million mass units. So they make these high contrast fringes, but they're not distinguishable yet from the classical curve. The classical curve, as you can see, and the dashed line lies exactly on top of the quantum curve. Because it wasn't the interferometer was not set up for this mass. It was set up for 200,000 mass units. And the cluster source just generated 2 big clusters, which is a good thing for the future. But now we still have to sort out what's happening. And so point number 1 is, if you look at the various clusters here of 100 kilodalton and a megadalton, this is their ionization energy, and that is not so much different. And if you ionize them with deep ultraviolet laser light of 4.6 electron volts, you can get essentially any charge state. And that is why we had these supermassive clusters in the mass spectrometer at the range where we expected 100 kilodalton. So it was actually either 7-fold 700 kilodalton or 10-fold megadalton cluster. And now that is our current challenge, and I hope that in the next very few days and weeks we can sort this out, just going to different laser powers and laser wavelengths to discriminate between different charge states of the different clusters. Not super trivial, but we have a plan and think we can do it. And the funny thing is that now we have to go to lower masses to make sure that we can really distinguish quantum and classical. That doesn't mean that what we've seen is not quantum also, because it's just the same. Quantum and classical have the same curve for these super high masses. And you can still extract something also from the megadalton fringes, in the sense that you can say, well, sorry, I come to what we can say. It's just to show where we're in the plot. So currently we probably have 2 massive things, and we have to make them less massive to be in the curve where we can clearly distinguish quantum and classical curves. And only later we will upgrade the experiment to go back to this dot. But for that we have to make them slower, and we have to change also the grating period. And all this is being planned, but this will take a while. The faster path is to briefly go back to lower masses, only a few 100,000, and then it would be okay. But what we can already say from what we've seen, so what would destroy a quantum interference pattern, besides what people here in the audience would say gravity at some point? Of course, what can destroy an interference pattern is anything that transfers momentum. A kick with a molecule from the outside, a kick with a thermal photon from the outside, a kick from a thermal photon from the inside, a kick from a sodium atom evaporated from the cluster in free flight. And all these things, obviously, and that's the good thing about the experiments, are proven not to occur. We see high contrast even at a megadalton in a regime where we didn't expect it and where we hadn't planned to be, so we have to go down to lower masses. But we know already for the higher masses, the really detrimental effects that would kill the experiment at higher masses, collisional decoherence, thermal decoherence, evaporative decoherence, they just don't occur, not with the conditions of the experiment that we have set. And now it depends a bit on the time, so I cannot go into the details here, but if you have questions, we can talk about this. So you can estimate the number of sodium atoms that can evaporate at a certain temperature. You can estimate what thermal spectrum you might have just with the huge number of vibrational modes that you have in a cluster of tens of thousands of atoms, and still you don't expect any vibrational decoherence, and we don't see any. Collisional decoherence we can manage by going currently only down to 10 to the minus 9 millibars, which is moderate. It's not a super good pressure, but it's enough, as you can see. So the question is how to move on to higher and higher masses. Currently, we still have to go back to, say, 200, 300,000 to make this 1 point. But then we will go, and lasers are being prepared to shorter wavelengths to handle even shorter de Broglie wavelengths. And we're working on slowing clusters to get to the 30 meters per second velocity range. Then I think we can also safely go to 1 million mass units and distinguish quantum and classical clearly. So this is only an outlook because my time is over. So what we have seen is perfect, so in agreement with theory, interference of organic materials in the range of 28,000 mass units, which happens to be exactly the mass of a green fluorescent protein. So the question is, why not do it also with a protein? And we're working on that. We are pretty advanced with our sodium cluster interference. And there's, to me, no doubt that this will be done very shortly and even up to a megadalton. And then the question is, if that works, so why not do it with a virus or viroid? And the smallest viroids are in the mass range of 100 kilodalton. So that's an interesting challenge, and we are tackling this too. Yeah, all the bio stuff I will skip because time is already over. So I just get to the outlook. So that's what we are looking into right now, where we want to proceed on the one hand with the metal clusters, transitioning also to dielectric clusters in the next generation of experiments. We can try to push quantum microscopicity to higher masses or higher values. There are interesting condensed matter questions that we could answer probably, or study at least, on phase transitions in nanomaterials and how to use that also for lithography. Proteins is a big thing, but super complicated, much more challenging because of sources and handling and availability, but also very promising in terms of avenues for spectroscopy and folding studies. And if it goes to higher and higher masses, well, then in the end, we also go back to nanoparticle cooling, optomechanical effects. We've learned quite a bit from Markus Arndt's group. Uwe Stierlich in particular was very supportive there also. And we're making progress with nanoparticles also, but there we are more interested in rotational quantum states, which have certain advantages that we can discuss. They don't need gratings, for instance. And so the scalability to even higher masses could be interesting. Okay, at that point, I should probably stop, and yeah, I'm happy to take any questions.
Okay, thank you very much.
Oops.
Yeah, we have time for 1 or 2 very quick questions. So I saw you and then John. Yeah.
You mentioned Schrödinger's cat, but how about Wigner's friend? Can you make these molecules process information in some elementary way? Just sort of
well, yes and no, but probably in your sense, no. So they are internally in a thermal state. Of course, you could say they're isolated in that sense. They're Hamiltonian systems, unitary systems, but they're not initialized by us. So it's difficult to bring them into a state where they can really process information that is useful. That's the short answer. And the more complex answer is if you put it, suppose you can put yourself into our interferometer. I would have to isolate you so well that you wouldn't see where you are. So there's no which part information that you could process. Otherwise, I've set up the experiment wrongly.
Okay, thank you. Yeah,
Okay.
a short
On,
question.
on your macroscopicity parameter, is there any assumptions about what would cause the deviations from quantum mechanics behind that, or is it just kinematic in some sense?
It's really generic. So there's no assumption. Actually, it turns out that, for instance, if you look at continuous spontaneous collapse, and if you look at gravitational collapse, they all follow the same mathematics. So they all are described by the same, if you wish, also macroscopicity, because they do a momentum kick or position kick, mostly momentum kick. So anything that perturbs the center of mass motion has to give a position kick somehow, and therefore all mechanisms are included, including unknown or unobserved dark matter scattering or things like that.
Okay, thank you.
Okay, so I understand we still have some questions, but in the interest of time, I will invite all of those that wants to ask Markus to ask him, I mean, in a different opportunity. So thank you
Yeah.
very much, Markus.
Yeah, it was a pleasure.